And I'm pretty sure this is on page 8 of your unit handout. This is still under the heading of 11.1 permutations, which, as I said in the video that I left for the sub on Friday, some of the problems you did in yesterday's lesson are combinations and some are permutations. I don't like the way they've structured it in the textbook, but the fundamental counting principle is not just about permutations, even though it's in that section, okay? Today what we're going to do is continue to work with more permutations, and we're going to be looking at factorial notation officially. Solve problems involving factorial notation and what are called permutations. So to begin with here, this is going to be fairly straightforward. If we take a look at, how many books do I have here? 7 books, and we're going to arrange them, thank you, on a shelf in a row, you should know what the answer to this question is in terms of how many different ways there are to do this. If you use the fundamental counting principle, then, you have 7 decisions to make. Which book is going to go first, which book is going to go second, etc. But I think we've graduated, even though you haven't been taught this officially in yesterday's lesson, in the last lesson, we've graduated to the idea that that's just 7 factorial. And I think under most circumstances that are like this, under all circumstances that are like this, you shouldn't need to consider the fundamental counting principle. You should have learned it's the number of items factorial. So once again, in this particular situation, 7 with an exclamation point is not pronounced 7. It's 7 factorial, and it means 7 times 6 times 5 times 4 times 3 times 2 times 1. So in general, and I want to give you a second to read this and contemplate what it's saying, in general, n factorial will always be n multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3, all the way down the line until you get to 3 times 2 times 1. And all this is saying is you take the argument of the factorial, which is n, and you multiply it by the number that's 1 less than it, and you multiply by the number that's 1 less than that, and you just keep subtracting 1 each time until you can't subtract 1 anymore. Well, maybe I should rephrase that, until you get to the number 1. And I'm telling you that n is a whole number, which means n can be 0, 1, 2, 3, 4, etc. And you might be interested to know what 0 factorial is, because 0 factorial doesn't fit this definition. But go ahead and calculate 0 factorial on your calculator. And just in case there was somebody who was away on Friday, or somebody who's maybe forgotten where to find that, you go to the math menu, you scroll over to what's called the probability menu, and I think it's the 4th option down. When I do that, I just go math, and instead of scrolling to the right 3 times, I just scroll to the left once, and it takes me there. So 0 factorial is defined. It's equal to 1. And later on in the lesson, I will explain to you why it's equal to 1. That doesn't really make sense, does it? So calculate each of the following. The first 2, 5 factorial and 7 factorial, you might even know. How many of you know 5 factorial is 120? Okay. If not, you don't have to memorize those things, but you go to your calculator. Make sure you know how to calculate that this is 120. The number that sticks in my brain for 7 factorial is 5,040. How many of you have come across that enough times that you think that's what it is, maybe? Not yet. Okay. You might. And if you don't, it's not a big deal. And what I would like everybody to do is calculate what 100 factorial divided by 98 factorial is. You're not allowed to divide 100 by 98 and say the answer is 2. This isn't 100 over 98. It's 100 factorial over 98 factorial. Now, how many of you have put that into your calculator and are slapped in the face with a domain error of some kind? Okay. The reason is that factorials grow so quickly. It's like that 25 factorial in that example with the desks. I think we had an example on Friday where we had 25 desks. The number starts to get quite big. And it's either 68, 69, or 70. What happens is, I know 70 for sure will break the bank. When you go 70 factorial, you're going to get an error because 70 factorial is greater than what your calculator works with. Your calculator will only be able to display numbers that are smaller than 9.99999 times 10 to the 99, which is a really big number. So 70 factorial is bigger than that. However, does anybody know what 100 factorial over 98 factorial is? What is it? 9,900. Why should that be? Whoops. Well, go ahead and explain it, Hunter. What's your thinking there?
When you get 100 factorial, it's everything from 100 underneath. But when you divide it by 98, it takes away from the 98 and below.
Right. So the 100 factorial is all of the factors in 100 factorial. That's why it's called a factorial. All of the factors in 100 factorial are 100 times 99 times 98, 97, etc. But all of those factors in 98 factorial are contained in all of the factors of the 100 factorial. And another way to look at it, I mean, I'll write this a couple of ways. It's an important enough idea that we don't want to just gloss it over. This is 100 times 99 times 98 times 97 times, I guess I don't need a multiplication sign, dot, 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 times 3 times 2 times 1. And it's over 98 factorial, which is 98 times 97 times 96 times dot, 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 3 times 2 times 1. And essentially, this, well, not essentially, it's a fact, that is equal to this. And we're talking about factors, and you're allowed to cancel factors that are common to the top and the bottom. So when you do that, all you're left with is the 100 times the 99. I'm going to go one step kind of deeper and say to you that 100 factorial over 98 factorial is 100 times 99 times 98 factorial. Right? And it's really good if you can think that way. That 100 factorial means you start off with 100, you multiply by 99, and then you go, well, wait a minute. Everything else after that we're multiplying by is 98 factorial, and I stop there and write 98 factorial because I see a 98 factorial on the bottom. And just to, put a lid on this and move on, I don't need the brackets. I just put the brackets because. And it doesn't matter where you put the brackets. On the top, it's 98 factorial in brackets. On the bottom, it's 98 in brackets factorial. That doesn't matter. The point is, the smaller factorial will always be contained in a bigger factorial. Okay. So, we extend this now to questions like the following. Simplify this expression. What do we get when we simplify this expression? Well, we say to ourselves that n factorial is a bigger factorial than n minus 3 factorial. You with me on that? N minus 3 is a smaller number than n, so n minus 3 factorial must be a smaller number than n factorial. So just like I expanded the larger factorial here until I could get my eyes locked on the smaller factorial, I'm going to do the same thing with this one. I'm going to take this n factorial and write it as n times n minus 1 times n minus 2 times n minus 3 times n minus 4. Now I realize I probably gave you limited space there. No, I gave you lots of room. All the way down to 3 times 2 times 1. And I just want to caution you here. Do most people need to write all of this to get to the answer? No. Should you write this on a written response? Yeah, you should. I think it shows a good understanding of factorials. This is now over n minus 3 factorial. And this is just another way that I like seeing students work. I'll show you the alternate way in a second. What I do then is I do the following. What I say to myself is that this is n minus 3 factorial. Sometimes what I will do instead And we're talking here about writing stuff down so that somebody who's marking your exam, whether it's me or somebody in Edmonton, looks at it and says, this person knows what's going on. You could also do this. Right? Just some indication that you're saying, well, that whole thing, starting at the n minus 3 going down to the 1, is n minus 3 factorial. So you can now cancel this with this, and the answer to this question is n times n minus 1 times n minus 2. I think maybe the higher end student is the way to put it, might do this. And that's perfect. There's nothing wrong with that. I'm always leery about people who are sitting in an office building at the University of Alberta on the third day of marking exams, marking the same question over and over and over again. And maybe they stayed out too late the night before and they're not in that great of a mood. And I think when you write a written response, you should do your best to try to make those people happy. Anyway, this is the answer. What about n plus 2 factorial over n factorial? Well, this time, we're not going to expand the n factorial because n is smaller than n plus 2. We're going to expand the n plus 2 factorial until we see where the n factorial is. And I'm perfectly aware most of you know where the n factorial is going to be. But it's a little bit different. When I expand the larger one, I'm going to have n plus 2 times n plus 1 times n minus 1. So my definition that I gave you at the top of the page for n factorial is for n factorial. It's not for n plus 2 factorial. We have to use common sense here. I'm not done, by the way. That the argument is n plus 2, and then we subtract 1, subtract 1, subtract 1, and you keep subtracting 1. So if I take 1 away from n plus 2, it becomes n plus 1. Take another 1 away, it becomes n. Then it starts creeping below n. And again, I really like writing this 3 times 2 times 1. And we all know you don't need to write 1, right? Mathematically, it doesn't matter, but I like it. And then on the bottom, we have n factorial. Well, this is n factorial. So this whole thing cancels, and you're left with that statement. And maybe you want to expand it, because maybe there's a little tiny piece of a question that says n plus 2 factorial over n factorial can be written as a n squared plus b n plus c. What are the values of a, b, and c? And you look at that and go, well, I don't know what to do. You do what I've tried to teach you in this whole course. You do what you can with the math that applies. You simplify that expression and see what happens. Any questions with B? All right, n factorial over n times n minus 1. Well, we don't have 2 factorials, so it isn't that a smaller factorial is contained in a bigger factorial, but these 2 factors, not factorials, the factor of n and the factor of n minus 1, will be contained as factors in the n factorial. And we start to expand the n factorial, and we can see those factors immediately, can't we? And then it's n minus 2. Well, I'm just going to write n minus 2 factorial. So think about that. I could write that the top is n times n minus 1 times n minus 2 times n minus 3 times n minus 4 dot, 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 times 3 times 2 times 1. But as soon as I get to that n minus 2, that's going to lead all the way down to the bottom where we have 3 times 2 times 1, I can just put n factorial. And then we have n and n minus 1. So this time, you have individual factors canceling, and you're not left with factors, you're left with a factorial. And the factorial here is n minus 2 factorial. We're okay with that? Okay. solve each equation. Well, this is the natural progression of things, is now that you know how to cancel factorials, you should be able to take an equation that has factorials and get rid of them. Before I go on, though, I want you to understand that if you had an equation and one side of the equation has this, you can cancel those a's, right? Because they are factors. Are you with me? Okay. And let's just say this is equal to c. If I multiply both sides by a times this delta symbol or triangle, whatever you want to call it, I can still cancel those a's. I'm just pointing out a very elementary fact about canceling things in an equation. You can cancel things if you have a factor over a factor in a term, but you can also cancel things when you have a factor on one side and a factor on the other side that are identical. So what are we going to do here? Is yours written this way, or does yours have a factorial symbol on the x minus 1? It's written this way? Okay. There should be a factorial there. If there, and I apologize for that. If there is no factorial there, then you're going to end up with an equation that has a factorial, and you can't solve that. So when you look at these two factorials, n plus 1 factorial and n minus 1 factorial, n minus 1 is smaller than n factorial, or than n plus 1. So we're going to expand the larger factorial. On the left-hand side, this is n plus 1 times n. And I'll just ask the question. How many of you see on the left-hand side it's n plus 1 times n minus 1 factorial? If you don't, I'll write it down. We subtract 1, etc., down to 3 times 2 times 1. And this is equal to 6 times n minus 1 factorial. But n minus 1 factorial is this. And that's why I gave that little mini lesson at the beginning that, you know, if you have a factor over a factor, you can cancel them. But if you have a factor on one side and on the other side you have a factor, you can still cancel them. So these go. And what you're left with now is n times n plus 1 equals 6. You're left with a grade 11 equation. I say grade 11 because it's going to be quadratic. We distribute the n through multiplication, and we get n squared plus n minus 6 equals 0. Now you're in very comfortable territory. I think that's factored correctly. So mathematically, you're getting n is equal to negative 3 and n is equal to positive 2. But we cannot take, we have to check for extraneous roots. It isn't that because n is negative we throw it out immediately. We want to make sure, just like with logarithms, that when we put our solution in, we're not left with taking an operation that we're not allowed to take. So when we put our n in, the argument in both of these factorials must be a whole number. And when I put negative 3 in, neither one of them is whole. And it doesn't matter, even if 1 is not a whole number, it's out. But 2 will work. So this is the answer. And this we can say is extraneous. We would have to explain that on a written response. Are we okay with that one? All right, another one. Well, we have a factorial on the top, we have a factorial on the bottom, and we need to solve this. Given that there was a printing, typing error, whatever you want to call it in the previous question, can you confirm that this is what you have, including the factorials? Okay, thank you. So I'm going to expand the larger factorial on the left once again, I will just say verbally what's happened here. N factorial is n times n minus 1 times n minus 2 times n minus 3 times n minus 4 all the way down the line. But that means that that n minus 3 all the way down the line is n minus 3 factorial. And what we end up with is over n minus 3 factorial. And this is equal to, we might as well expand this out. Sorry. 2n times n is 2n squared. 2n times 8 is 16n. And now we can cancel this. And be in more comfortable territory in that the equation we now have does not have factorials. So what do I have? I have n times n minus 1 times n minus 2 equals 2n squared plus 16n. It's looking as though, unfortunately, we're going to get a cubic polynomial function. But I'm going to show you how we can cheat the system here, okay? Because we know the solution must be a whole number. We can use our calculator. If I expand this out, actually, you know what? We're not going to have to cheat the system. So I've just, and I'll show you why we're not going to have to cheat the system in a second. When I expand the n minus 1, n minus 2, I get n squared minus 3n plus 2. I still need to multiply this n in and get n cubed minus 3n squared plus 2n is equal to 2n squared plus 16n. It is a cubic polynomial, but the constant term is 0. There's no plus 8. So going back to the polynomials unit, to solve a polynomial equation, you have to zero it. What am I going to get? Minus 5n squared minus, I think, 14n. My subtraction right? 2n minus 16n is negative 14n. I've got my n cubed. I've got negative 3n squared minus 2n squared. Looks good. So the reason why we don't have to worry about synthetic division or anything, we can factor out an n. So we kind of lucked out. When I take n out of n cubed, it becomes n squared. N out of an n squared becomes an n. N out of an n becomes a constant. And now I can write this as n times n minus 7 times n, whoops, better, times n plus 2. That means we have three solutions. N is equal to 0, n is equal to 7, n is equal to negative 2. We need to look at the original equation. I got to pull it down up here, n minus 3. The original equation is this. 0 is out. Not because we're not allowed to take the factorial of 0, but if you put 0 in for n, you'll have 0 minus 3 factorial, and negative 3 factorial is not defined. So 0 is out. Negative 2 is out for obvious reasons, I think, so the answer to the question is 7. All right. So now we're going to talk about permutations. And the first part of this part of the lesson is going to go really quick. I'm just trying to train your mind into thinking of what we've already learned as being sometimes a permutation. Sometimes. Bobby Bear was not a permutation. Bobby Bear went to his closet and he could pick his pants first and then his shirt, or he could pick his shirt first and then his pants. Right? Did we have an example in Friday's lesson about the ice cream and the waffle and regular cone? That was a combination. You just pick that item, pick that item, pick that item. It doesn't matter the order that you pick them. As soon as we got into questions where you were arranging people in a line, that's a permutation. That's not a combination. Are you with me on that? Okay. So now we're going to talk about permutations. A permutation is simply an arrangement of a number of items. Since permutations are arrangements, order is important. When you arrange things, the outcome is important. When you arrange flowers, you don't just put all the flowers in the vase, you put them in a particular arrangement, in a particular position. And we use the following notation to describe permutations. When you see NPR, which is how it's pronounced, what it's telling you is you have n items, and you're going to find out how many arrangements there are of R of them. So if I said, what is 8p6? I'm saying if I take these 8 people, how many ways can I arrange 6 of them in a line? Which is not 8 factorial. If I said this, that would be saying how many ways can I take these 8 people and arrange all 8 of them in a line? That would be 8 factorial. But 8p6 is saying how many ways can you arrange the 6 items? This would be like me saying I have 8 different cookies on the table, and my mom has told me I'm allowed to eat 6. How many different ways can I eat those 6 cookies? I can eat the snickerdoodle first, and then the chocolate chip, etc. And you have to eat a whole cookie in order for that analogy to work, right? You can't eat part of a cookie and move around. Okay, that's not what we're after. So, example 3. And you already know how to do a lot of these questions, okay? You're not learning anything new in terms of solving problems. You're learning something new in terms of how to think of them. How many permutations of all of the letters of the word Regina are there? First of all, yesterday I would have just said, how many ways can you arrange the letters? Well, we know that this is, how is my counting skill? That there are 6 letters. So if we drew 6 blanks and approached it with the fundamental counting principle, we'd say 6 times 5 times 4 times 3 times 2 times 1. But we know that's 6 factorial. However, there's absolutely nothing wrong with writing this as an answer. You can do that. How many permutations of all of the letters of the words Pink Floyd are there? Well, 4, what do we have here? 9 letters. That would be 9 factorial. Or we could write 9p9. And I've never actually looked. I don't know why. I guess I should look one day. I like saying permute, as if permute is a verb. I don't know that it actually exists. But when I say 9p9, I mean 9 permute 9. I mean 9 arrange 9. But I use the word permute. How many permutations are there when putting 7 books on a shelf? Well, this is getting annoying right now. 7 factorial or 7p7. But I think you know me by now. I don't often do something unless I find a value in it. I'm just trying to implant this in your head. How many permutations are there of n items arranged all at once? Well, we're leading up to something here. It's that, right? So A through D are simple. We already know how to do that. We're just formalizing things by talking about permutations. How many 3-letter arrangements can be made using the letters from the words Roxy Music? Well, there are 9 letters there. Am I wrong? That's right? 9? So if you approached it with the fundamental counting principle, you would put 3 blanks because you only want to get a 3-letter arrangement, and you would say the answer is 9 times 8 times 7. 504? 504. But that means that 9p3 must be 504, right? We can check that out on your calculator. I don't know if you've noticed this, but on your calculator, when you go to the math menu, by the factorial function, there's an NPR function. And on my calculator, this is what it would look like. I would enter 9, then I would go to my math menu, probability sub menu, and choose this, and then put 3. And you get 504. There are 7 different cookies, and you're allowed to eat 4 of them. How many different ways can you eat them? Well, this is where we abandon the fundamental counting principle. We say to ourselves, we know how to use it if things get complicated, like the boys and girls have to alternate, or the word must start with a vowel, or something like that, or Joan and Emily have to stand together. Then there's no simple thing here. You just use the fundamental counting principle. But here you go 7p4. Just 210, I think. No? 840. Thank you. So you get 840. And if you use the fundamental counting principle, that's what you would get. So now the question is, how do we get... Well, let's do one more. This is I really wish you already knew about combinations, and then I could explain to you a better way to think of this. There are 8 empty seats on a bus, and 6 people get on the bus. How many different ways can they be seated? See, the issue here is you're not arranging 6 seats out of 8. You're arranging 6 people in 6 seats that are chosen out of 8. But this is still going to be 8p6. And I will demonstrate it to you by approaching it this way. When those 6 people get on the bus and they're looking at those 8 seats, how many different seats can the first person choose? 8, right? So this is going to be 8 times 7 times 6 times 5 times 4 times 3. And I'm leading up to something very important here. This is the same as 8p6 in the same way, I'll leave this frozen up here, that this is the same as 9p3. This first number goes here, and we put 3 different numbers leading down. But we don't include, and this is important, we don't include the 6 times 5 times 4 times 3 times 2 times 1, right? That's not in there. I want you to notice that this is 6 factorial. And I want you to notice that 6 is 9 minus 3. When we go to this one, let me get rid of this now. This does not include 2 times 1, which is 2 factorial. And 2 happens to be 8 minus 6. So what does that tell us? If we wanted to know what NPR is, which is what question 8 is asking, it would be n factorial, but we do not want to include a factorial that's the difference between the 2 numbers. So we divide by that difference factorial, or the factorial of the difference. This is a formula. It's on your formula sheet. All right, let's finish off this lesson. There's the formula in all its glory. NPR is n factorial over n minus r factorial. How many different arrangements are there using 4 letters from the word Ashmont? Okay. All you want is the answer. How's my counting? Are there 7 letters? It's 7PR. And Noah's going to calculate what that is. 840. Or, I guess what you could do is you could say, I'm going to use the fundamental counting principle. And you could manually enter 7 times 6 times 5 times 4, which is going to be 840. Or you could say 7p4 is 7 factorial over 7 minus 4 factorial. And I know that some of you might say, why would I want to do that when I can just get the answer? Because later on you can't. It gets more complicated. And what this becomes is 7 factorial over 3 factorial. And if you do what we did at the beginning of the lesson and expand the larger factorial, you will see that the 3 factorial cancels, and you're going to be left with that. Are you with me? Okay. Quick note here. I already told you that 0 factorial is 1, right? 0 factorial is 1. Why is that? It's by definition, really. You know that that's n factorial. How many ways are there to arrange 8 people in a line all at once? Well, 8 factorial, 8 times 7 times 6, etc. So how many ways are there to arrange n people all at once? N factorial. We know that has to be n factorial. But according to the formula, the top of this is n factorial, the bottom is n minus n factorial, and you're left with this statement, that this answer is supposed to be equal to n factorial over 0 factorial. Well, how on earth can that equal, how on earth can this give us n factorial? The only way it can happen is if 0 factorial is 1. All right. One last question. This is the final example, correct? Okay. So in a particular country, license plates consist of 2 letters followed by 4 different digits. Find the total number of possible plates using the fundamental counting principle and permutations. And by the way, the letters have to be different. So fundamental counting principle, letters, numbers. I hope these first 2 entries don't blow your mind. 2 different letters. While there are 26 letters in the English alphabet, I guess maybe the question could have said, but we can't use an O or an I, in which case it would be 24 times 23. But there are 26 letters for the first entry and then down to 25 because you cannot repeat. And then I hope this isn't a big shock to your system. 3,276,000, yes? Okay. So 3,276,000 different plates. If you do it with the with the permutations idea, it becomes, I think, simpler. It becomes that. Because, and we're using the fundamental counting principle here. We're just not writing out a whole bunch of blanks. We're grouping the thing into 2 main tasks. You must arrange 2 letters out of 26, and you must arrange 4 digits out of 10. So if you put this in, if you go 26p2 times 10p4, you're going to get the same number. And you may very well see on an exam this number for an answer, or you may see this number. It could be a numerical response question that says, the answer to this is 26PA multiplied by BPC. What are the values of A, B, and C? So it isn't necessarily important that you know the numerical answer, but you know how to do the math. So you can see a number of questions. There are some questions dealing with factorial notation to open up the assignment, and then it turns into practice with permutations. The answer to number 8 should be 140, not 120.